So, can we construct more images that satisfy boundary conditions that turn, really hard problems into trivial ones? And the answer is yes. One of the things you have to remember, though, is when particles are mirrored, they have to have the negative charge of what they'd have otherwise. Negative charge of the thing they're reflecting. So here's another problem that you can solve with the image method, the mirror method. So let's say you have your coordinate system like this, okay? And then you have a conductor sphere. And then away from that, a distance s away, you have a charge, right? And the conductive sphere as well as infinity are both potential 0. They're both grounded. How you can ground the sphere, I don't know. Maybe you set up a wire and then later on you remove the wire and so it stayed at that potential. So how do you solve this? How do you solve for solving the potential for everywhere but inside the sphere, right? And, well, obviously inside the sphere the potential is 0, because on the outside of the sphere it's 0 and it's a conductor. So the solution is you take and you introduce a new image, minus q. You ignore the sphere, okay? And then you construct a new image there. And so now for any point P, you have both the original charge and the negative charge inside that sphere. And the exact charge of the inside charge is, the charge is going to be negative r over s times q. Okay, where radius is r is the radius of the sphere. And the position it's going to be is at r squared over s. Okay, and how somebody came up with that, I don't know. Whoever figured that out, I'd like to talk to them to see how they figured it out, because it's one of those problems that the solving is much more difficult than the checking that it's true. And it turns out that these two conditions will basically give you the potential of 0 on the sphere. I'm not going to work through that problem. That's problem 3.6. It's one of those problems that hopefully will help you understand better how to solve your own problems. Notice that since the charge is always inside the sphere, like for any s outside the sphere, it's going to be smaller. It's going to be inside. And that has the effect of, this charge doesn't come out of the sphere and screw up your boundary conditions. You know what I mean? So it's kind of cool that way. The force between the two is rather easy to calculate, although rather mystic when you try to understand exactly what it's trying to say to you. And to be honest, this is one of the reasons why I'm late with these videos is I'm arguing with Griffiths. He's not here, but I'm arguing with his text, and I think he has it wrong. So if I'm wrong, you can correct me in the notes, in the comments below. But if I'm right, you can congratulate me for being right. So his math. So when he calculates the force, so he says the force is going to 1 over 4 pi epsilon naught times the two charges q prime divided by, I think I know where I went wrong now. I forgot that the q prime was not the same. Anyway, let's walk through this. I spent like 30 minutes on that and I felt like a jerk because I couldn't figure it out. So what happens here? So 1 over 4 pi epsilon naught. We have the original charge times minus r over s and another charge. So that's q squared r over s. All over s minus and a is r squared over s squared, right? Well, if we multiply the top and the bottom by s squared, so we multiply the top by s squared, so we have minus q r s, and then multiply the bottom by s squared, so we can bring it inside the square now. So we have two s's on the inside, minus r squared, and there's your answer. That's the answer that he came up with. And again, I shouldn't put the negative sign there. I should put it out here so the whole thing's negative. So, I forgot a square sign. That's the force. Interesting note at the bottom, he says, had it been a cube instead of a sphere, the method of images wouldn't have worked for any Q, right? So you can't find a Q prime to put inside of a conducting box to make everything look happy. Anyway, this is one of those surprising results from electrodynamics. It's one of those things that if you understand enough techniques, then hard problems become truly trivial to solve. So if you see a problem with nice symmetry, look for the method of images and try to solve it. Hope you had fun with this. I'll see you in the next section. Bye.